All right, so any compound with only one chirality center will always be a chiral compound. Okay, now remember, being chiral means that something is not superimposable on its mirror images. Again, like our hands, they are chiral. Okay, now if a molecule has more than one chirality center, a compound may not be chiral. It may have a plane of symmetry. So let's consider the stereoisomers below, which possess two chirality centers. The trans isomer is chiral, but the cis isomer is actually not. It's achiral. If a molecule has a plane of symmetry, it will be achiral. The reason that the cis isomer is achiral is because it can be superimposed on its mirror image. Molecules with an even number of chirality centers that have a plane of symmetry are called mesocompounds. Another way to test if a compound is a mesocompound is to see if it is identical to its mirror image. So if you draw the mirror image of the cis isomer and show it can in fact be superimposed on its mirror image. By definition, when a compound is identical to its mirror image, it is not chiral, even though it has chirality centers. Overall, the presence or absence of rotational symmetry is irrelevant to chirality. That's a type of symmetry where if you rotate it, it's the same. That means nothing to us. A compound that has a plane of symmetry, meaning you can fold it on top of itself and it's symmetrical, will be achiral. A compound without a plane of symmetry will usually be chiral. There are a few exceptions that we're not going to go into regarding an inflection point, but we're going to kind of bypass those because they're so few and far between. A compound with chirality centers, but is achiral because of the symmetry, again, is called a mesocompound. The molecules that are listed here below are mesocompounds. You can see that mesocompounds have, in fact, a plane of symmetry. In our first molecule, there's a plane of symmetry right there. Sorry about that. But second one, we've got a plane of symmetry right through the molecule right there. And in the third one, I've got a plane of symmetry right there. Okay, again, the plane of symmetry can actually even go through an atom as long as you can half that molecule and fold it in on itself and have it be symmetrical. Finally, we're going to talk a little bit more about classifying double bonds. Okay, so we talked a little bit about the cis and trans classification of double bonds. There are only very specific situations where you can use cis or trans. You have to have two of the same group on each carbon of the double bond in order for cis or trans to work. So if you look at our example over here, we have two double bonds that are clearly different. They're orientated differently in space, but we have no cis or trans configuration because we don't have two of the same thing on both of the carbons. For these types of molecules, we can designate them as being either E or C, okay? And so what we have to do is look at each carbon of the double bonds and look at the two groups that are attached to it, okay, that are not part of the double bonds. We're going to use those same Kahn-Ingold-Prelog rules, and we're going to give each group a priority. Again, we're basing it on the atomic number of the atom directly attached to the carbon. So I can see for my left-handed carbon, I've got a fluorine directly attached and a carbon directly attached. Fluorine's got the higher atomic number. That's my number one priority. The ethyl group with the carbon will be number two. On the right side, I have a nitrogen directly attached and a hydrogen. Nitrogen has the highest atomic number. That is priority number 1. If my priority 1 or top priority groups are on the same side of the double bond, as you see with the molecule on the left, we call it the Z configuration. My organic professor used to like to say Z same side, so you would remember it that way. If the 2 higher priority groups are on opposite sides of the double bond, it is the E configuration. E standing for antigen, which means opposite.